Welcome back to another video. Here, we will talk about chi-squared confidence interval on a single sample. Here, we want to define a confidence interval on the variance of a normal population. So, our goal is to find lower and upper bounds so that probability of the population variance being between these bounds is 1 minus alpha. Please note that here we are exclusively talking about working with samples from normal populations. Let's assume that we have a random sample of size n of independent observations from the same identical normal distribution. Then the statistics defined as n-1 multiplied by sample variance divided by population variance follows a chi-squared distribution with n-1 degrees of freedom. Let's work with a chi-squared distribution as shown here. I will push half alphas to each tail. Given that the area under any probability density function is equal to 1, the area between chi-squared values of alpha over 2 with n-1 degree of freedom and 1 minus alpha over 2 with n-1 degrees of freedom should be equal to 1 minus alpha. As this should work for any random chi-squared variable with n-1 degrees of freedom, we replace the chi-squared term in the parentheses with the statistic of our choice. To isolate the population variance, we invert the ratios within the parentheses, which also flips the inequality signs. Next, we multiply all ratios within the parentheses with n-1 times sample variance to isolate the population variance. This gives us the general two-sided confidence interval formula on the population variance. To define this confidence interval, we need to find the sample size, sample variance, and two chi-squared values either using Python or chi-squared tables. Let's go over an example together. Students have participated in a survey regarding their height. We are tasked to find a two-sided 95% confidence interval on the height variance of the students. In order to do so, we need to find the sample variance and two chi-squared values. To find the sample variance, we need to calculate the sample mean first, then find the squared difference of each observation and sample mean, sum them up and divide it with 29, which gives us 265.3. We retrieve the chi-squared values using Python or chi-squared tables. Once we have all the necessary information, we can plug them into the formula and report the confidence interval. Alternatively, we can load the confidence interval chi function, pass the arguments, and report the corresponding confidence interval. We can also define one-sided confidence intervals on the population variance. These intervals only bound the variance on one side, either the upper bound or the lower bound. You can see the formulas for the two one-sided confidence intervals on the population variance here. Thank you for listening to this short lecture on chi-squared confidence intervals on a single sample.